last few questions in Chapter 7 are more mapping questions, but they're mapping multiple genes at once. This first problem, number 27, is showing how to take a whole bunch of individual mapping data and to use that and put it into a map. This is a nice looking problem. It's because it looks pretty complicated at the beginning. There's just all these random numbers and it's not really clear what you're supposed to do with them. And so, but once we get through it, you'll see it's pretty straightforward. And the key is that we need to remember that all of these are test crosses. So these are all 2-point test crosses. And in a 2-point test cross, which is always a double heterozygote cross to a double homozygote, which is a test cross, if we get 50% recombinant, the genes are unlinked. If we get less than 50%, genes are linked. So we can quickly look through these things, and anything that says 50 is those two genes are unlinked, and anything that says less than that, they're linked. So we go through A and B unlinked, A and C unlinked, A and D linked. So what does that mean? So we're going to put those together. And we can actually put the distance on there. So we might as well do that. Instead of putting a comma, we can say A. So A and D are linked with 12 map units between them. A is also linked to G with 4 map units. And B and C are linked, but let's go and see. But A is not linked to B, and B and C are linked. So that means B and C are a different, what we call this a linkage group. So B and C, because they're linked together, B and C are linked together 10 map units apart. They're in their own linkage group. B and D are not linked. B and E are linked. So B and E are 18. And they're linked. And because B and C are linked and B and E are linked, then C and E need to be linked because they're all on the same chromosome. B and F not linked. B and G not linked. C and D not linked. C and E linked. 26. So C and E are linked at 26. That makes sense. B's linked to C. B's linked to E, so C should be linked to E. So we're just sort of putting them in groups now, and then we'll figure out the overall map. C and F not linked. C and G not linked. D and E not linked. D and G are linked. So that makes sense. D and G are linked over here. So D and G are linked over there. D and G are 8 map units. So these are just our individual distances between these genes, and then we can use them to put together a map. And then the rest of them are all unlinked. E and F, E and G, F and G are all unlinked genes. None of them are linked. So let's make a map of these guys. So we know A and D are 12. A and G are 4. So G, we could put G down here because A and G are 4. Or if A and D are 12 and A and G are 4, it's possible that G is down here. If it's down here, we would expect D and G to be 16, but D and G are 8. In this case, we've got A and D are 12, and D and G and A and G are 4, and D and G are 8. So that makes sense. So that means this is not the right map. And this one's right. So I'll rewrite that one a little bit, get rid of some of those scribbles. And we can have our map here. A and D are 12. And G in the middle is 4. And then D and G are 8. Again, we don't really know what direction. This way we know it's AGD. It could be DGA, and we can't really tell the difference at that point. These guys are not linked to the other ones. So we got B and C as 10. B and E is 18. So now 18 could be down here. We'd have 18. If we had that, then C and E should be about 8, right? If B and E are 18, C and E should be about 8. But we see that C and E are about 26. So that's more consistent with E being down here. So C and E are 26, that's this big long distance. And B and E are 18. And those are consistent numbers. So 10 and 18 are 28, and this distance is 26. And the numbers aren't always super accurate. It's not, we're not like measuring with a ruler, we're measuring with recombination frequency, and that's not the most precise thing in the world. And also, as genes get far apart, the mapping gets a little bit less accurate. In fact, as genes get far apart, when you map those genes that are far apart, the numbers usually come out a little smaller than you'd expect. So you'd expect 28, but we got 26. And I'll show you how chromosomes, how the crossing over happens in chromosomes and how that causes us to get less numbers. But that would be, so that's our map for these two things. This is one map. This is the other map. That's it. So that was pretty cool. So you can map them all, but that's like doing a whole bunch of crosses. So here we can do, this is another one of those 3-point crosses. And we just have to kind of go through the process that we've gone through before. And there's no substitute for, substitute for practice here. So we've got, what do we got here? We got waxy, shrunken, and yellow. Why a yellow is a V, I don't know. But we got waxy, shrunken, and yellow. So first thing I like to do is find my parents. These are the most. So these are the parents. That means that waxy, shrunken, and yellow go together, or at least the capital letters all go together. And then the mutants all go together, the little guys, little WX, little SH. And these letters are a little goofy. So, if I got goofy letters, I like to change them. So, that just is goofy. So let's just do W, S, and V. So we're going to have big W, big S, big V, over little w, little s, little v. So we would call that the parental configuration or arrangement of alleles. We don't know what's in the middle yet. To see what's in the middle, we have to look at the fewest. The fewest are W, so our double crossovers. I'll put these in a different color just because we can. So our DCOs are 87 and 94. These are our smallest. So little w, little s, big V. And big W, big S, and little v. Now does that look like what we should get? If we got a double crossover, we'd get little w, big S, little v. and we'd get big W, little s, big V. So that's not quite what we get. So these are in a different order. So the way to figure out what order we're in is to compare these two guys and see which letters have to switch sides across the line to go from our parentals to our double crossovers. Well, big W, big S, and big V start together. And now here it looks like if V switches sides, now little w, little s is with big V. So that means that big V and little v switched. So that means V is in the middle. So we can rewrite this as V in the middle. So we know that the three capital alleles started together. That's what we got just from looking at the parentals. But comparing the parentals to the double crossovers tells us that V is in the middle. So now, if we get a double crossover, we would get big W, little v, big S. Big W, little v, big S. Alright, so that's our order. Big W, big V, big S, over little w, little v, little f. So now we know the order. Now we can calculate the distance between W and V. And then we look for our single crossovers. If we get a single crossover, we get big W, little v, little s. So big W, little v, little s. We get little w, and then big V, big S. Little w, big V, big S. These numbers, so just waxy, or just big W by itself is this guy. So it's got two little sh, little v, big W, and then the ones that are similar in number always go together. So we're talking 292 plus 280 plus the double crossovers have to always go in there. The distance between V and S. So we can, I'll write this over here again so we can try to follow those things through again. Now we're looking for a crossover between V and S. Big W, big V, little s. Little w, little v, big S. So the ones that look like that are going to be big W, big V, little s. Little w, little v, big S. If we look up here, those numbers are big W, big V, little s, so 1515. The other one, 1531. Now, if you're confident in what you've done so far, and you know, and you've figured out these numbers, and you think those are crossovers between W and V, and we figured out our double crossover numbers, and we know our parentals, then we know that we only got two numbers left over, so we can use those. So if you're confident and you're kind of in a hurry, you can just put those together. Always add in the double crossovers, because the double crossovers also involve a crossover between V and S. And then you add those all up. Plus 87 plus 94 is 753 divided by 10, 756 is 0.07. So W and V are 7%. The other ones are 1515 plus 1531 plus 87 plus 94 equals 3227 divided by 10, 756 is 0.30000, so it's VS is about 30%. So to draw a map, we would go WV is 7. This isn't exactly the scale, but V to S would be 30. And that is a 3-point mapping.